Hey everyone, welcome! So today we're skipping the easy stuff and diving straight into the deep end with partial fractions. We're going to tackle two of the trickiest cases out there, those pesky quadratics in the denominator you just can't factor, and what on earth to do with those top-heavy fractions. Ready? Let's do this. You know that feeling, right? You're staring at a problem and there's a denominator you absolutely cannot break down. It's like a brick wall. Or maybe you've seen a fraction where the power on top is bigger than the bottom, and you're just like, what now? Well, if that's you, you're in the right place. We're going to solve that mystery for good. So here's the plan for today. We'll kick things off with the theory for case 3 and case 4. But we won't stay there long. We're going to jump right into some practice exercises from the textbook, and then ramp it up to an exam-style challenge to make sure it all sticks. Okay, first up, case 3. This is your go-to whenever you've got a proper fraction, but hiding in the denominator is a quadratic, an x-squared term, that is just stubbornly refusing to be factorized. All right, so here's the big change, the key rule for case 3. Normally, right, you just stick an a on top of a factor. Easy. But for these non-factorizable quadratics, the numerator has to be 1 degree lower. That means it's not just a constant anymore. It has to be a linear expression, a bx plus c. Honestly, if you remember one thing about this case, make it that.
Theory is one thing, but seeing it work is another. Let's take a look at this worked example. The expression is 8 plus 2x minus x squared over x minus 1 times x squared plus 2. See that x squared plus 2? That's our guy. It's unfactorizable. So boom, we know we're dealing with a classic case 3 problem.
So, how do we solve this thing? It's all about a smart mix of substitution and comparing coefficients. First, we set up our fractions, a over the simple x minus 1 part, and bx plus c over our quadratic x squared plus 2. Now, here's the clever bit. Our first move is to plug in x equals 1. Why? Think about it. It completely knocks out the bx plus c term, because 1 minus 1 is 0. That gives us a instantly. So cool. After that, plugging in x equals 0 is another great shortcut to help find c. And for b, the last piece of the puzzle, we just compare the x squared terms on both sides. It's a system, and it works every time. Okay, so that's case 3 sorted. Now let's pivot to our second big challenge, case 4. This is all about improper or top-heavy fractions. And what that means is the power of x on top is either the same as or even bigger than the power on the bottom. It's a really easy check, actually. Look at the proper fraction here. The degree on top is 1, the bottom is 2. Top is smaller, so it's proper. Simple. Now look at the improper one. Degree 2 on top, degree 2 on the bottom. They're equal, and that's the rule. If the top's degree is greater than or equal to the bottom's, it's improper, and that means we have to do something else first. And this is the absolute key. You cannot, I repeat, cannot just start finding a, b, and c if you have an improper fraction. It just won't work. As Maths Genie puts it perfectly here, your first job, your #1 priority, is to do algebraic division. This is what turns it into something manageable, a whole number part, plus a new proper fraction. And it's that proper fraction that we can finally decompose. Let's check out this worked example to see how it works. We've got 2x squared plus 5x minus 11 over x squared plus 2x minus 3. Degrees are both 2, so yeah, it's improper. And look, what's the very first thing they do? Polynomial division. That division gives us a 2 plus a remainder of x minus 5 over the same denominator. All of a sudden, we're left with a much friendlier proper fraction to solve. So you can think of this as a simple 2-step recipe. Step 1, divide. That takes your big, messy, improper fraction and splits it into a nice whole number part and a proper fraction. Step 2, decompose. You just take that new proper fraction and break it down like you normally would. But there's one thing everyone forgets. You have to add that whole number from step 1 back in at the very end. Please don't forget that final step. Okay, theory's done. We've covered both cases. Now for the fun part, let's get our hands dirty and actually solve some of these problems from exercise 7b. I promise this is where it all starts to make sense. Okay, let's kick off with question 4a. Now the first thing you should always do is check the degrees. If you multiply out that denominator, you get x squared plus x minus 2. So we've got a degree 2 on top and a degree 2 on the bottom. What does that tell us? Yep, it's improper. And that means our first move is non-negotiable, algebraic division. And here's what the final answer looks like. See that structure? You've got the whole number 2, which we got from our long division, And then you have the two smaller fractions, which are the decomposed pieces of the remainder. That's the classic look of a case 4 answer. Okay, question 5 is pretty cool. It's like a combo problem. First, it's improper, degree 3 over degree 3. But look closely at the denominator. That x squared means it also has a repeated root. The question is actually giving us a massive hint with the form they want. That single a all by itself, that's screaming I came from long division. And the b over x plus c over x squared, that's the textbook setup for a repeated root. Now, solving this one, it does take a bit of careful algebra, not gonna lie. Once you've multiplied it all out, you've got to play a matching game with the coefficients for every power of x on both sides. It's a little tedious, but if you're systematic, it'll lead you straight to the answers. A is 2, b is -3, c is 4, and d is -1. All right, feeling warmed up? I hope so, because we're about to ramp up the complexity. The next set of problems are multi-parters. They make you combine a few different skills before you can even think about partial fractions. So question 6 throws a curveball right at the start. We have to figure out our own denominator. Part A says, hey, factorize this cubic first. So that means pulling out the factor theorem. You know, testing simple numbers like 1, -1, 2, trying to find one that makes the whole thing 0. As soon as you find one root, you can divide it out and then just factor the quadratic that's left over. And once you've done that and you have your denominator fully factorized into x plus 1, 2x minus 1, and x minus 2, part B suddenly becomes, well, just a standard case 1 problem. You set up your a, b, and c over the 3 factors, solve, and bam, there's your final answer. Now, question 7 looks like it's the same deal, but there's a little trap here. You start factorizing the cubic, you find that x equals 3 is a root, great. But then, when you divide out that x minus 3 factor, the quadratic you're left with, it can also be factored by x minus 3. So what does that mean? It means our denominator is actually x minus 3 squared, 2x plus 1. We've got a repeated root on our hands, and that means the setup has to be a over x minus 3, b over x minus 3 squared, and c over 2x plus 1. You get that right, solve it out, and you land on this answer. The whole key to this problem is spotting and correctly setting up for that repeated root. And here we go, the final boss of the exercise, question 8. This problem is awesome because it pulls everything together. We're given this polynomial, but it has these unknown a and b coefficients. So step 1 is to use the factor and remainder theorems just to find out what a and b even are. Only then can we factor the polynomial, and only then can we finally do the partial fractions. So you go through the process, use the theorems, find out that a is -4 and b is -3, and then the polynomial factorizes really cleanly. The last step is a big partial fraction calculation, sure, but it's just a standard case 1 at that point. And it all boils down to this nice, elegant result. Wow, we've just worked through some seriously tough problems. Before we call it a day, let's just do a quick fire round on a couple of classic exam questions, just to make sure those core skills are locked in. Okay, here are 2 very typical exam questions. For both of them, what's step 1? Always factorize the denominator. The first one becomes x plus 1, x plus 2. The second one becomes x minus 3, x plus 2. And from there, they're both just simple, straightforward case 1 problems. It's a perfect reminder, always figure out what case you're dealing with before you do anything else. So let's do a super fast recap of the big rules. See a quadratic you can't factor? The top needs to be bx plus c. See a fraction that's top-heavy or improper? Your very first move is always long division. Got repeated factors? You need a separate fraction for each power of that factor. And what's the foundation for all of this? You've got to be a pro at factorizing that denominator. Let's end on this thought. We've spent all this time learning how to smash these complicated fractions into tiny, simple pieces, but why? Well, one of the biggest reasons is calculus. Just think about it. How much easier would it be to integrate 3 simple little fractions instead of one big, monstrous one? That, right there, is where this amazing algebraic skill really becomes a superpower. Thanks so much for joining me.